E. So Schwarzschild is most conveniently depicted in a Penrose diagram, which I'll draw. Penrose diagrams are very helpful for the people who know them. However, it's not necessary to understand Penrose diagrams to follow what I say. So there's an asymptotic boundary which can be attached to Schwarzschild called future null infinity. And the black hole exterior region is characterized as the causal past of this asymptotic boundary. And we will consider just the region R strictly bigger than 2m. And this exterior is not the entirety of the Schwarzschild manifold. It's bounded to the future by a complete event horizon, R equals 2m. And observers can live in this exterior region and remain causally unaffected by what happens beyond the event horizon in the black hole interior. So the most basic question that one can ask about this family is the exterior region non-linearly asymptotically stable as a solution of the vacuum Einstein equations? So in these lectures, I'll talk about a theorem, which is joined with Dafermos, Holzegel, and Rodnianski. Last year. And the theorem says, yes, Schwarzschild is stable in the exterior.
Some people who say that yes, I have it set to the mic. Okay, yeah, no, it's working.
Okay.
Yeah,
okay. So the exterior of Schwarzschild is non-linearly asymptotically stable as a solution of the vacuum Einstein equations. So for small perturbations of Schwarzschild, the corresponding solution possesses a black hole. Observers can live forever in the exterior. The black hole remains close to the Schwarzschild which was perturbed and decays to another member of the Schwarzschild family at inverse polynomial rate. Now, if you have any familiarity with the subject at all, you'll know that there's only one sense in which this theorem can possibly be true, and that's if it's true modulo Kerr, or let me say, to a codimension 3 set of perturbations. Okay, so as is well known, Schwarzschild is a subfamily of the larger Kerr family. And the Kerr family is more complicated, and accordingly it was only discovered much later in 1963. And because it's more complicated, I'm not going to write it down. But this describes a black hole as long as A is less than or equal to M. And when A is equal to 0, this is exactly the Schwarzschild family. Moreover, it's stationary. So Kerr with A small is a small perturbation of Schwarzschild. And because it's stationary, it obviously doesn't converge back to a member of Schwarzschild. So this theorem is full finite codimension stability of Schwarzschild, or stability modulo Kerr. The reason for this number 3, so Kerr is a 2-parameter family, Schwarzschild is a 1-parameter subfamily. You might think that this should be codimension 1. However, it's more convenient to, in order to parameterize smoothly, it's more convenient to overcount, in which case we think of three not as we think of Kerr not as a 2-parameter family, but as a 4-dimensional family. So you can think, if you take a member of Schwarzschild and you'd like to describe a nearby member of Kerr with the same mass, one not only has to prescribe an angular momentum parameter, but one also has to prescribe an axis around which the Kerr black hole is rotating. So angular momentum together with the axis is 3 parameters in total. Hence, this is a codimension 3 statement. So I'll state a more precise version later in the course. There's been a huge number of previous works. This is a problem with a very, very rich history, particularly in the physics literature, where the works date all the way back to the 50s. I'll mention some of those later in the course. Let me just first here mention some mathematical works. So the first nonlinear stability theorem for the vacuum Einstein equations in this asymptotically flat setting without any symmetries is the celebrated proof of the stability of Minkowski space. So this is due to Christodoulou-Kleinemann. From the early 90s. Subsequently, there's been many later works. Schwarzschild, stability of Schwarzschild has been studied in symmetry classes. So by far the simplest symmetry classes are those which reduce it to a 1+1 dimensional problem. There are some older works of Christodoulou from 87, Dafermos, Rodnianski. From 2005, and also the PhD thesis of Holzegel from 2010. So 1+1 reductions it simplifies quite dramatically. Anything beyond a 1+1 dimensional reduction is considerably more involved. So beyond 1+1, there's only one such work, and that's a nice work of Kleinemann and Jeftel on this problem in polarized axis symmetry. From 2018. And one can also study this problem for Einstein equations with a positive cosmological constant. And the analog of the Kerr family is the Kerr-de Sitter family. And this was studied in the very slowly rotating case by Hinz and Vashi in 2016. So there's many more relevant works, which some of which I'll mention as we go, but unfortunately I don't have time to mention all of them, so I apologize to anyone who I miss. There's also been many extensions to Kerr, and I'll also talk about those a bit later, maybe on Friday. So in the lectures, I have the following brief plan, which I currently intend to stick to, but we'll see how time permits. So today, I'd like to talk about the linear wave equation on a fixed Schwarzschild background. So this can appropriately be viewed as a poor man's linearization of the Einstein equations around Schwarzschild. Tomorrow, I'll talk about Einstein equations in double null gauge. And the linear stability of Schwarzschild. In the third lecture, we'll go on to nonlinear stability of Schwarzschild. And on Friday, I'll end with some conclusions and an outlook. And I'll hopefully have time to mention some open problems. So today, we begin with the linear wave equation on a fixed Schwarzschild background. And this, as I say, it can be appropriately be viewed as a poor man's linearization of the Einstein equations. So the poor man's linear stability problem is the problem of showing boundedness and decay of solutions to this equation. So the linear wave equation on a fixed Schwarzschild background. Boundedness and decay for solutions which arise from smooth localized initial data. So this problem in itself also has a very rich history. One can make statements about fixed mode solutions, so one can rule out exponentially growing mode solutions of this equation. Beyond statements about fixed modes, the study of this problem was initiated by Wald in 1979. And since then, there's been a huge number of works, particularly in the last 15 to 20 years. And this culminated in a work of Dafermos, Rodnianski, and Schwarzschild. And that's from 2014. So we now understand this problem not only on Schwarzschild, but on Kerr for the entire subextremal range of parameters. And there have been many people contributing between. There's works of Blue Soffer, Blue Sturbans, Tataru Tuhanianu, Anderson and Blue, and many, many others. So this problem, many of the most fundamental difficulties to the stability of Schwarzschild actually appear already here. And an equation like this comes up naturally in the nonlinear analysis, we'll see later. So I'll spend today discussing this. And this problem, it's a very nice illustration of the dual geometric analytic nature of the vacuum Einstein equations. So this is an inherently an analysis problem to show that solutions of a partial differential equation are bounded and decay. But the way we show this is to exploit in a quantitative manner several geometric properties of Schwarzschild. So let me describe those properties. So the first is called the Redshift Effect. So if we have two observers in the exterior of Schwarzschild, observer A crosses the event horizon, and observer B crosses the event horizon at a later advanced time, then the frequency of signals sent by A will be exponentially shifted to the red when they're received by B. And this exponential redshift has a damping effect on waves, which will be exploited. So the redshift effect, you should think, is in the context of this problem, it's our friend. It's a good property of Schwarzschild. The second is the presence of trapped null GD6. So in Schwarzschild, there are null GD6 which neither cross the event horizon nor escape to infinity, but they orbit the black hole forever at the photon sphere at r equals 3m. And the presence of such trapped null GD6 is a potential obstruction to the decay of waves. So we'll see r equals 3m appear as a potential obstruction. So unlike the redshift effect, which was our friend, trapped null GD6, you should think are our enemy. And the third is the phenomena of superradiance. And this is relevant only in the case of Kerr with non-zero rotation. So let me not spend time discussing this now. So the proof of boundedness and decay, which I'll follow, so I should say I'll follow the presentation here, will follow a set of Clay lecture notes of Dafermos Rodnianski. And the proof of boundedness and decay goes by capturing these geometric features of Schwarzschild via appropriate vector field multipliers and commutators. So to discuss vector field multipliers and commutators, it's helpful to introduce the language of energy momentum tensor. Okay, so this is the goal for today, to show boundedness and decay of solutions in this equation. So if we take a space-time, mg, and the function on that space-time, we can define the energy momentum tensor associated to this function, which I'll denote Q. Okay, so the energy momentum tensor has the property that it's divergence free if C solves the wave equation on this spacetime. So more generally, the divergence of Q is equal to this. So now, if we take a vector field, we can define an associated J. And this is defined by contracting the energy momentum tensor with the vector field X. And so if we take the divergence of this one form J, we get a term where the divergence falls on Q, and that will give us X applied to Psi and box of Psi. And there'll be a term when the divergence lands on X, and what appears then is exactly deformation tensor of the vector field X. Okay, so in particular, if psi solves the wave equation, and if X is a killing vector field so that its deformation tensor vanishes, then this gives rise to a conservation law. So more generally, we can define, if we take a function, we can define a modification of J, which at first looks slightly strange. I'll tell you where this comes from. So this is defined to be J plus these modified terms. Okay, and where does this come from? Well, if we take the divergence of this and we integrate over some space-time region, then one gets, well, the first thing will be a term like this. So we multiply the wave equation by the vector field X applied to psi. And there'll also be a term arising from this modification, which is the function W times psi times box G of psi. Okay, so you should think energy estimates come from, there's two ways we can arrive at energy estimates. We can either multiply the equation by a vector field X applied to psi and integrate by parts, or we can multiply by a function times psi and integrate by parts. So these corrections account for this second thing. So we will get then an integral over the boundary of R of this current contracted with the normal to that boundary, the appropriate normal to that boundary. And then there'll be another space-time term arising first from the deformation tensor. And then there'll be some more terms arising from these modifications. And they look like this. Okay, so everything I'll say this afternoon involves choosing an appropriate X, choosing an appropriate W, and integrating over an appropriate space-time region. So for example, a standard example is the conservation of energy for solutions of the wave equation on Minkowski space. So if we consider Minkowski space, which is R3 plus 1 together with the Minkowski metric. I'll also use polar coordinates a lot later. So this is the unit round metric on S2. So if we take the space-time region R to be that between t equals 0 and t equals some capital T. If we take the vector field X to be d by dt, which is a killing vector of Minkowski space, and this function W we just take to be 0, then if psi solves the wave equation, this left-hand side will vanish. We chose W0, so these two will vanish. And d by dt is a killing vector field, so its deformation tensor vanishes, and we just get left with these boundary terms. And the two boundaries are t equals 0 and t equals capital T. So we get this conservation law. Okay, and you can compute what QTT is, and you see it's just the standard energy density. So this is the standard conservation law for the wave equation.
Why are we ignoring the side
yeah, so I just want to ignore technicalities. So I mean, one would have to assume that C decays initially, and then okay, you would show that there's no contribution from those. Okay, are there any other questions? So of course, to see this conservation law, one could just differentiate this and see that one gets 0 by the equation. However, it's quite elucidating to formulate it in this geometric language like this. So why did this work so well? Well, first, d by dt is a Killing vector. So why do these boundary terms that we get look so nice? Well, the reason is because d by dt is time-like, and the normal to these hypersurfaces is time-like as well. So these are space-like hypersurfaces, so the normals are time-like. And that's a general property. So if we take two future-directed time-like vectors, x and y, then when we contract the energy momentum tensor with these two vectors, we get something which is comparable to the local energy density. So let me just write it like this. So if you fix any coordinate system, this object, energy momentum tensor contracted with two time-like vectors, will be comparable to the sum of all first derivatives squared. So you see the reason this worked so well is we're contracting here Q with d by dt, which is time-like, and then the normal to this hypersurface, which is again d by dt. So it's typically, I mean, we typically like time-like Killing vector fields because this term vanishes and we get good positivity properties. Okay, so the decay, so remember the problem is to show boundedness and decay of solutions of the wave equation on Schwarzschild. And the way we do this is based on a method which was introduced by Dafermos Rodnianski, and it's called the R to the P method. So we take some space-time which satisfies some appropriate asymptotic flatness property. And we're interested in showing decay of solutions to this equation. So it's a method for showing decay the solutions of this equation. So the method takes as an input two ingredients. So for solutions of this equation, the first ingredient is boundedness of a non-degenerate energy. So I'm going to phrase it like this. So, I mean, you can think that this is modeled on Minkowski space. So for this discussion, you can have Minkowski space in mind here. And boundedness of a non-degenerate energy means we take some foliation of the space-time by hypersurfaces sigma t. So for the purposes of this discussion, you can have in mind these t equals constant hypersurfaces in Minkowski space. Strictly speaking, that's not exactly correct, but for the purposes of this discussion, you can have this in mind. So then we take the energy measured by some strictly time-like vector field n. We would like to show that this is bounded by the corresponding energy on sigma t1. Okay, so here n is a uniformly time-like vector field. So for example, then if these hypersurfaces are space-like, that means that this energy is going to be comparable to the sum of all first derivatives. So this is the first ingredient, and I'll call that a non-degenerate energy boundedness. And this obviously you should think of as a boundedness statement. The second is integrated local energy decay. So this is slightly more complicated. So one looks at the energy only confined to some compact set. So since the space-time is asymptotically flat, there'll asymptotically be some r coordinate, and we restrict to some large ball. And we look at the integral in time of this energy, and we would like that integral in time to be bounded by the initial energy by a constant that can depend on this radius r. Okay, so you can think of this as like some sort of weak decay statement for the energy in this compact region. So the energy in this compact region, the integral in time of it is finite. So of course that doesn't necessarily mean that it decays, but you can think that it does decay in some sort of weak sense. And this is for all r. And sometimes, as in the case of Schwarzschild, to show a statement like this, one has to lose another derivative on the right-hand side. So we'll allow for having more derivatives of c appearing on the right-hand side than what appear on the left-hand side. Okay, where n again is this time-like vector field. So this we call an integrated local energy decay statement. And the method takes these two ingredients and then produces a decay statement. And the type of decay statement, if the space-time was Minkowski space, looks something like this. It looks like r to the 1/2 times c is bounded by some D, which D is some initial weighted energy of the solution C, divided by, let's say, 1 plus T minus R, or alternatively RC bounded by 1 plus T minus R to the 1/2. Okay, so the process of going from these two ingredients to the decay is quite general, and it doesn't use special properties of Schwarzschild. So this step uses, it's again all in the language of vector field multipliers and commutators. So it uses as multipliers the vector field R to the P times dt plus dr, and W is equal to 1 over R in the asymptotic region, where everything looks like Minkowski space. So, and P here is between 0 and 2. So we call it R to the P method because of this step, which goes from these two ingredients to the decay statement. The properties of Schwarzschild feature in establishing these two ingredients. So for the rest of today, I'm going to just talk about how to establish these two properties in the case of Schwarzschild. Yeah. That's what the rest of the talk's going to be about.
No, not 1 and 2, but the decay.
Oh, the decay. Yeah. So it involves dividing the space-time into a near region and a far region. In the far region, everything looks like Minkowski space, and one uses this hierarchy of multipliers in that far region. Then there's one can show that, so I wanted to avoid this, but so one shouldn't really think of these as being T equals constant hypersurfaces in Minkowski space, but they are hypersurfaces through which the energy in fact decays. So T equals constant, we have a conservation law in Minkowski space. But in the method, one chooses these to be hypersurfaces through which the energy in fact decays. So the R to the P hierarchy leads to a decay statement for these energies. And then, okay, by Sobolev inequalities, then one gets to these pointwise statements. But this is all, it has not very much to do with Schwarzschild itself. The delicate properties of Schwarzschild come up in these, establishing these two. Are there any other questions?
Where does most of X come from? So you mentioned that you get some particularly good stuff when it's killing. So
why these? So these actually look a little bit like so they're not killing. And you should think, I mean, a similar thing will happen when we discuss the redshift vector field in Schwarzschild. So there's a sense in which these multipliers are actually better than killing. Okay, so the good property about killing vector fields was that they produced no term on the right-hand side. These vector fields, they actually produce a favorable term on the right-hand side. And it's this favorable term that one exploits to transform the hierarchy of estimates into a decay statement. So it's something very closely related happens in Schwarzschild when one tries to establish a boundedness statement like this. So I can comment on it further when we get to that.
what's the motivation for the W?
So that's maybe slightly more complicated. No, there's a slightly deeper reason, which I can maybe tell you after. I don't think I want to go into it. Yeah. Any other questions? So first, I'll just show how these go in Minkowski space, and then it will be helpful to compare them with what happens in Schwarzschild. I think this might be a good point to take a break, though. So maybe we can have 5 minutes, and then we'll do those two. So first, I just want to go through these two ingredients in the case of Minkowski space, because it's illustrative to compare when we get to Schwarzschild. So we consider a solution of the wave equation on Minkowski space, let's say arising from compactly supported initial conditions. So the first ingredient, the non-energy boundedness of the non-degenerate energy, this we've seen already. This arose from taking the time-like Killing vector field d by dt as a multiplier. So the first one is easy in the case of Minkowski space. So the second one is a little bit more complicated. But always the idea is choose an appropriate multiplier and use the energy identity. So the statement is for any delta, the following holds. And this is a bit easier in polar coordinates. So this integrated energy, which has these R weights, so it's a space-time integral of these energies with R weights, which decay as R goes to infinity. They're bounded by the initial T energy. Okay, of course, so here, this nabla slash is the angular gradient. So these are polar coordinates, and then nabla slash is the angular part of the derivative. So of course, one needs some degeneration in R weights because if these weights were all one, this object would be conserved, and hence its integral in time is certainly not finite. Okay, but the statement is with these decay in R weights, this is true. In particular, if you restrict to some compact subset in R, then certainly one has a statement like this where one actually doesn't need to lose any derivatives on the right-hand side. Oh yeah, sorry. So T here is this vector field d by dt. Yeah. So this I could alternatively write as this standard energy. Yeah, there's a constant. That's okay. It depends on delta. So the constant blows up as delta goes to 0. Indeed. Okay, so the proof involves choosing a multiplier. So first one takes the space-time region 0t cross R3. But there's a technical issue with polar coordinates, so one should remove the neighborhood of the origin. So this region looks something like this. Then one chooses the multiplier x to be d by dr, to be 1 over r. And then you'll see what appears is, so this is not killing anymore. It's certainly not a killing vector field. So there'll be a space-time term produced in that energy and in the identity. And the space-time term produced is exactly this one. So then there'll be boundary terms. The boundary terms will be things on this cylinder. Those go to 0 as epsilon goes to 0. Then there'll be boundary terms on these two hypersurfaces. And because this vector field d by dr, it's not a time-like vector field anymore, those will not have a good sign. However, they can be controlled by the energy identity. So this choice of multiplier controls this first term. And then, okay, one can choose some more multipliers. And I mean, the difficult part is beginning, but once you have one term now, when you choose a new multiplier, you're allowed to, you allow for that to appear as an error term since you've already controlled it. So the claim is you get those remaining terms.
What are the kinds of x's that you have to choose?
Similar things like 1 over r to the 1 over r to the 1 plus delta times this. Okay, so that's Minkowski space. So let's go now to Schwarzschild. So the standard TR coordinate system, in which I wrote down Schwarzschild at the beginning, is actually not the most convenient one, given that it degenerates at the event horizon. So it's actually more convenient to write Schwarzschild in a different representation. However, the metric looks a bit less familiar. So if one defines this T star, then the metric in T star R coordinates looks like this. Okay, so you see, I mean, you recall before there was a term in the metric which blew up when r is equal to 2m. This is actually a completely regular expression across the event horizon r equals 2m. So the pictures like this are those like Penrose diagrams. T star equals constant surfaces look like this. And the time-like killing vector field, the stationary killing vector field in this coordinate system is d by dt star. And if we compute the length of this with respect to g, we see that it's time-like as long as r is strictly bigger than 2m. However, it becomes null on the event horizon. So the first thing we could do in Schwarzschild is use this killing vector as a multiplier. And we like it because it's killing. We like it because it's time-like, away from the event horizon. But the fact that it becomes null on the event horizon is something that we don't like. I guess this, we could call it a degenerate energy boundedness. So so if you just compute what the terms that this multiplier will give you on these hypersurfaces, on C's we get something that looks like this. Good control over the dt star psi term. Good control over the angular derivatives. The d by dr derivative, the transverse derivative to the event horizon, it does appear, but it appears with a degenerate weight. Okay, and this is bounded by the corresponding thing initially. So proof. Use dt star. So right, so right. Maybe this is confusing. Let's go there. Thank you. So this falls short of that ingredient exactly because of these weights which degenerate as r goes to 2m. And again, the presence of these weights is not surprising given that the vector field becomes null as we go to the event horizon. And in fact, if all you know is this conservation law, this is completely consistent with the transverse derivative blowing up along the event horizon. And in fact, this is what happens in so-called extremal black holes. This is the famous Aratakis instability. So to overcome that degeneration, one has to exploit a further property of Schwarzschild. And the convenient property to exploit is the redshift effect. So we remove this degeneracy by exploiting redshift effect. And this redshift effect we capture in a vector field multiplier. So there's a vector field with the following properties. So there's R1 bigger than R0 bigger than 2m, which you can think of as close to 2m, and a vector field n, which is uniformly time-like, future directed, and let's say it's T star invariant, so it looks the same as you vary T star. And it has the following properties. So it looks like the killing vector field when you're far away. And so it's just like this. So if this is R0, this is R1. So it's equal to the Killing vector field away from the event horizon. Close to the event horizon, it has this good property. So this, if you recall what appeared in the energy identity, it was the divergence of the current J. And when we're close to the event horizon, this term actually has a good sign. So it's not zero just because n is not killing anymore. I mean, it can't be killing if it's time-like at the event horizon. But you should think it's better than killing. The bad term, it actually has a good sign. So it controls the energy. And this is only true close to the event horizon. So it looks something like this. Okay, the existence of such a vector field, I mean, the construction, so again, this is from these lecture notes of Dafermos Rodnianski. The construction is actually very general. The property of Schwarzschild that it really relies on is this redshift property. So there's this construction is not special to Schwarzschild. Okay, so one now to show the energy boundedness. One uses this redshift vector field n as the multiplier. Yeah, you can write it explicit. It's just it's not like a delicate thing. It's something that just looks like I drew in the picture. So I guess this is the non-degenerate energy boundedness. Well, it's the same statement, but without the degenerations. Okay, so proof. Use so as we say, there'll be these space-time terms now. In the region, I mean, we have these three regions. So when R is bigger than R1, N is a Killing vector field, so there's no space-time term. When R is close to 2m, these terms have a good sign. So they're actually favorable. And we only have to worry about what happens when R is between R0 and R1. But R0 is strictly bigger than 2m, and this degenerate energy provides good control there. Okay, so this provides good control of the solution when R is in this region between R0 and R1, where this could in principle have a bad sign. Okay. So that's the proof. T star, yeah.
It doesn't matter that normal is coming.
The normal is not becoming null.
Oh, the normal's not becoming.
No, the normal, it's a uniformly space-like at the surface. Yeah.
And it's defined, sigma tau is defined up to the right.
Exactly, yeah. Yeah. Okay, any more questions? So that's the non-degenerate energy boundedness.
You showed us that proposition to show us how the degeneracies appear when you choose this, and then you showed us this one to tell us, well, that's not a problem. You just choose n like this when you get rid of it. Or is there something that I'm missing where you're using this somehow to do that?
Right. So it's both, right? So it is helpful to just see how it degenerates. However, remember, there's this region where we don't know anything about. So this is what the term looks like. We know it's good in the region where R is close to 2m. We know it's good when we're far away because it's killing, but we don't know anything about what happens in between, right? But in between, we use this one. Yeah. And I should say as well, so it's a similar, the R to the P d by dv multiplier. It looks similar to this, but this is true close to infinity rather than close to the event horizon. So in some sense, you can think of that R to the P vector field as being the analog of this n vector field when you swap infinity in the event horizon. Okay. So then the next thing is to show the integrated local energy decay statement. And this is the claim. So let's call this is a degenerate integrated local energy decay. So remember, we said there were these two geometric properties which were relevant. There's the redshift effect, which we've just seen is our friend. The other one was the trap null geodesics, which we said our enemy, and they're going to feature now. So for any delta, this is the claim. Yeah.
Does it matter up to the event horizon?
Yeah. Yeah, up to and including the event horizon.
So you can have data there as well.
Yeah. Yeah.
And presumably you'd expect decay along the event horizon to be slower than because of the trapping. Then
no, not necessarily slower, no. So I mean, there's two trappings, right? There's trapping at the event horizon and there's trapping at R equals 3m, the photon sphere.
Yeah, well, that's the one I'm talking about.
The photon sphere,
yeah.
Right, so the trapping which happens at the photon sphere, it's actually unstable, meaning that if you take a null geodesic, which is trapped, and you perturb the direction ever so slightly, generically that null geodesic will not become trapped. And because that trapping is unstable, in fact, it doesn't slow down decay rates. It just means that, well, I'll show you in a minute what it means. So, so this is the claim. So there's an integrated decay statement. However, there's this factor which degenerates exactly at the photon sphere, R equals 3m. So it looks very similar to the expression that we had in Minkowski space. The only difference is that there's this factor which degenerates when R is equal to 3m. And this is bounded by some initial energy. So again, the degeneracy appears exactly at the photon sphere, and this is to be expected. There's a theorem of Sphyrski, which says that this statement, without that degeneracy, without any degeneracy at all, cannot hold. Okay, so some degeneracy there is necessary. So the fact that it's squared here is not optimal. You can make it weaker, but there has to be something there. So again, this is because high frequency waves like to localize along null geodesics. And the presence of the trapped null geodesic means that there's these high frequency waves which like to live at r equals 3m for long times. And this construction of Sphyrski involves such high frequency waves. There is an extra term which is controlled. Maybe I'll show you that in a moment. So the normal to r equals 3m. So if this is r equals 3m, the derivative in the normal direction, one can actually control this one without any degeneracy. I'll show you this in a moment. Okay. So now this falls short of the eyelid ingredient, right? Exactly because of this degeneration. So the ingredient for the method, it was this, but without that degeneration. So this still falls short of that. So the proof is choose an appropriate multiplier. And it's easier, it's a bit more difficult in these T star R coordinates. So one defines this R star, this rigid Wheeler R star. And then in, so not the T star, but in the T R star, one takes x to be equal to f of r times d by dr star. And then w, one chooses a bit differently now. So w and then f is something which looks like this. So f. So when one uses this multiplier, one will see three space-time terms. One will be exactly this derivative, this normal derivative, which appears with a good sign. The next will be the angular derivative, the nabla slash, which remember that was the first thing that we saw in Minkowski space. For that term to have a good sign, it's necessary that f changes sign at r equals 3m. So this is f, this is r. And the third term is the term c itself. So if, and that has a bad sign. So the easiest way to deal with that is assume that c is supported on high spherical harmonics.
Is that f prime in W?
This is f prime, yeah. So if it's supported on large spherical harmonics, then the angular term actually dominates. So this controls this. So it's similar to in Minkowski space. Once you begin with something, then it's easier to go back and get the rest. So one begins with these two, then the other derivatives, one goes back. Then the low frequencies one can do separate. Then, okay, when one does, so there's actually factors in here which degenerate at the event horizon as well. So then one goes back and revisits this redshift vector field. And remember that provided good, that it gave rise to good space-time terms. And that's everything. There are also constructions which don't involve decompositions into spherical harmonics at all. They're perhaps slightly less, when you're beginning, it's maybe slightly, this one's the easier one. The wave equation, which actually appears in the Einstein equations, is actually even a little bit nicer than this. And this step is something that's actually even a little bit easier for Einstein equations than it is for this wave equation.
Martin, the comment you made about degeneracy.
Yeah.
So what we have here is a proposition that tells us, choose n as you did, then you get this. Is the statement that there is no choice of n for which you will produce an estimate where you do not have degeneracy?
Right, exactly. So the statement is this, without the degeneracy, this statement is not true for all solutions of the wave equation.
Oh, so it's actually false. It's not.
Yeah, it's actually false.
Yeah.
Yeah. So this is the Sphyrski construction.
You said this is for when the low modes vanish. So how do you take care of that?
Yeah, so there's other multipliers that you can use for the, it's a little bit easier for them because then you don't have to worry about these angular terms anymore. But as I say, there is a construction which doesn't involve decomposition into modes as well. Okay, are there any other questions? So I'll just end. So remember, this still falls short of that second ingredient because of the degeneration. So the way that one overcomes that is by losing a derivative. So, one can remove this if there is another term on the right-hand side. If there is another derivative of C on the right-hand side. So remember, these constructions involve high frequency waves, and having terms with more derivatives on the right-hand side penalize high frequency waves. So the final statement is the full integrated local energy decay. Looks like this. The same, but without this degeneration. So one has no degeneration, but one has more derivatives on the right-hand side.
But you just lose one.
Yeah, and actually one, you can lose epsilon even if you're willing to go there. So this goes by exploiting the presence of this zeroth order term, which does not have a degenerating factor. So one can, for example, commute the equation with the Killing vector field d by dt star. So since this is Killing, d by dt star applied to psi is also a solution of the wave equation. So one can repeat, and then dt star psi will be the zeroth order term here. Okay, and similarly, Schwarzschild spherically symmetric, so you can also commute in Schwarzschild with the rotation vector fields. And okay, the remaining thing we actually didn't need to. There was actually no degeneration for that one in the first place. Okay, that's everything I wanted to say about this poor man's problem. Are there any questions? Yeah. Yeah. Here it's the whole thing, but we have these degenerating R weights. So of course, to go from this to the statement about a compact region is trivial if you're letting the constant depend on the size of the region. Yeah.
So I don't know what was your plan for the lecture, but you're not going to show us that commutation thing.
Oh, that's just a trivial thing, right? So if this is 0 and K is a Killing vector field, then this is
your comment about exploiting that first term.
right. So then one repeats for K applied to psi. Okay. So then what appears now is the same thing, but this is replaced by K psi, and this is replaced by K psi. So K psi is that extra derivative on the right hand side. Yeah, I'm using n, but just because n is, you can add extra terms if you want, but the claim is n actually controls all those extra derivatives that appear. But yeah, for simplicity, let's add extra things.
Just for more of a historical comment or a question, this method that you've shown us, that was the Dafermos Rodnianski.
Yeah.
And
this is a bit of a revisionist history.
the revisions.
Yeah.
And I mean, where you presented it, it's really elegant and clear. Like you've got this, method of generating these estimates. You can choose the vector field carefully and cleverly, and it just gives you everything you want. What was it like before that?
Oh yeah, it was much messier. Yeah.
Much messier.
Yeah. So actually, even in the lecture notes which I've followed, the lecture notes actually predate the R to the P method. Shortly after that. Yeah, I don't remember, but yeah. So as I say, I mean, we'll see tomorrow when we go to the full linearized Einstein equations, there is a wave equation which arises, and these observations from this poor man's problem will apply directly to that wave equation which arises there.
And I guess for the work you mentioned about higher P, this method is no longer the method that's used.
I guess it's like a refinement of this method.
Okay. But still, the idea of choosing vector fields carefully is still basically.
Yeah, and I mean, all of these things, I mean, this is the nice thing about this method is that it completely localizes the different issues which come up. So one first understands the redshift without worrying at all about what happens near r equals 3m. I mean, the vector fields one chooses there are completely designed, they're completely tailored to the event horizon to exploit properties of that redshift effect. Then here we use a new multiplier, which is completely tailored to r equals 3m. And okay, in that general step of going from those two ingredients to decay, that involved that r to the p multiplier, which was tailored to what happens near infinity. So these two things are the same. And
so I imagine that all of this, well, does this work for wave equation on Kerr as well?
yeah, it's more complicated to establish these two ingredients on Kerr. So we heard a bit yesterday about.
So the vector fields you have to choose just harder.
I mean, it's harder because, okay, there's this phenomena of superradiance, which I didn't talk so much about. So the Killing vector field, the stationarity Killing vector field in Kerr, it's not only, I mean, here it becomes null at the event horizon. In Kerr, it's actually space-like by the time one gets to the event horizon. So that means the conserved energy fails to have a sign at all close to the event horizon. And as A becomes large, superradiance and Traplin potentially become more and more coupled from one another. Become more and more coupled to one another. So one has to worry about potential coupling of those effects.
And in the end, similar estimates for Kerr are known.
Yeah. In the full subextremal range, we have for the wave equation and now Jokolsky equation we heard about yesterday, we have boundedness and decay statements. What's very interesting is the extremal case, actually. So I didn't talk so much about this, but when A is equal to M, so I said Kerr describes a black hole as long as A is less than or equal to M. When A is equal to M, that case is called extremality. And what happens there is very interesting. So the redshift effect degenerates. So there is no localized redshift. So there's no analog of this redshift multiplier. And in fact, axisymmetric solutions, one can show the transverse derivatives to the event horizon blow up along the event horizon. This is the Aratakis instability. Now, moreover, what happens outside of axisymmetry is presumably even worse. So in subextremality, superradiance and trap-in potentially couple to one another, but one can exploit the fact that they do decouple. In extremality, that decoupling degenerates, and we don't yet know how bad that is. So it's going to be worse than the axisymmetric case, but how bad it is a very interesting open question.
From the perspective of Kerr stability,
yeah,
why do we care so much about the extremal?
It's an interesting. Yeah. So extremality is often excluded from stability conjectures. Yeah. I'll also talk a bit more about this in the final lecture. Yeah. Yeah, so remember that I'm going to talk about the nonlinear problem. And if you want to try to implement something with the parametrics in a nonlinear problem, that's a nightmare. It's actually, though, I mean, it is more intuitive, I would say, to follow this method in the linear setting even. Yeah. Yeah. Any more questions?
In the acidic concept, when you
Yeah.
add a cosmological,
Yeah.
it's only going to help you.
It's only going to help you, yeah.
This whole, and so everything is just going to be the same, if not better.
I think these things are the same that I talked about, but what's much better is the part I didn't talk about with going from the ingredients to decay. Okay, so there's not really in the static region of Kerr de Sitter, there's not really infinity there. There's a cosmological horizon. So in fact, there is no restriction at p equals 2. And okay, one can actually infer exponential decay in that case. I mean, inferring faster than any polynomial decay is an easier thing. But then, okay, one can actually show exponential decay. The linear wave equation, there's a result of Holzegel, Smolevici, and they show that solutions decay logarithmically and no faster. So you could no faster than logarithmically. So you do have stability for this poor man's linear equation. However, on Schwarzschild ADS. However, we know, I mean, maybe I'll talk about this on Thursday. To upgrade a linear statement to a nonlinear statement, the borderline decay rate is 1/t. So 1/t you should think is borderline. 1/log t seems far too slow for a nonlinear, to have nonlinear stability. But this is another very interesting open question.
So the jury is still not on that one.
The jury is still on that one, yeah. But I would expect it's unstable. Yeah, 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 yeah. Okay.
Do you have any more? Is lecture one over?
Lecture one is over, yeah.
Oh, lecture one. I thought you So, any questions? I mean, I guess we all asked our questions already, but are there any other questions? So sorry, but can you explain how you can spend a derivative here to get rid of the?
Oh yeah, sorry, maybe I should have done this in more detail. So if psi is a solution, we also know that any Killing vector applied to psi is a solution. So for example, you can take d by dt star of psi. Okay. Then, okay, this statement is true if you replace psi by dt star of psi. Okay. So that means this derivative will appear here in place of psi without degeneracy. Right. So you'll also have these now second order derivatives with degeneration. But in particular, you'll have the first order derivative with no degeneration. Right, at the expense that now you have. So this is one derivative, but when you apply it to k psi, you'll have two derivatives on the right hand side.
No questions on